Uh, Good afternoon, everyone. Yeah, Simon Campbell here from Monash. I've only recently joined Astro 3D, and just like to thank the organisers for giving me a talk today. And today I'll be talking about some of the first stars, in particular at the low mass end, which may or may not have formed, as we heard from Gary before. But some of the higher metallicity ones, I've got this little asterisk at the top there. I'm just getting my laser. But some of the events that happen to these zero metallicity stars also happen at higher metallicities. So this work is done with a whole lot of collaborators over the years. In particular, I'll highlight Carolyn Doherty at the moment, and also Pranav Talwar, who's working with me on a Monash Honours project on this topic. Okay, so I'll just start off with talking about the halo stars. So Madeline just mentioned the halo before. This time we're looking at the halo field stars. These are sort of ancient fossil remnants in the galaxy, and they go down to very low metallicities. So what I've got here is carbon versus iron, both on H. And here I've got these are individual metal pole stars, and I've got a dotted line in here, which is the scaled solar line. And so you can see the normal, so-called normal metal pole stars sort of track this galactic chemical evolution pretty well. But it was noticed very early on that there's some strange things going on at low metallicity, and that is that there's a lot of carbon, and these are known as carbon-enhanced metal pole stars. So there's lots of these, and the frequency seems to increase as you go down in metallicity. This is quite an old plot, so the low metallicity end here has been really populated a lot better now by people like David Yong and Gary DaCosta here today. So the main takeaway message is that lots of carbon at low metallicity in these halo stars. Now there's a subset of these CEMPs, carbon-enhanced metal pole stars, that also have heaps of neutron capture elements, so very heavy elements. So here we've got barium on Fe versus europium Fe. This is from Bhate et al.'s study in 2015. They're in two groups here. So we have this group called CEMP-S. So these are carbon-enhanced metal pole stars, but also with S-process signatures. And this is very well explained by AGB star nuclear synthesis, which we've heard a little bit about today. And the idea is that these stars are in a binary system, and the slightly more massive star went through the AGB phase, produced S-process elements, and then transferred some of that onto the halo stars that we see today. Now, these blue stars up here are less easy to explain. These are known as CEMP-SR. And they were designated SR because they seem to have characteristics of abundances similar to S, but also with additional R. And one idea was that they formed an environment with enriched R process abundance pattern, and then S was added to that later, possibly by AGB stars. But if you do the detailed models of this, you can't actually reach this quadrant in this diagram. So this is a bit of a mystery, these CEMP-SR stars. So the summary there is observational, just a very simple summary of these halo stars. There's lots of carbon, and some of them have a lot of heavy elements. So now move on to the modeling. So this is sort of harking back to my thesis eons ago. I'm getting back into it because it's of more interest now with these heavy elements. So I'll talk about a 0.85 solar mass star, zero metallicity, so POP3. And this star would have a lifetime of about 10 gig years. So it may have been one of these binary companions that has polluted the halo stars we see today. So just as a general overview, I've got an HR diagram here. Two stellar tracks. The red one is what I'll be calling the normal star, and POP3 is the blue track there. So normal being sort of global cluster metallicity. And both these stars have the same mass, so 0.85, and so all the difference will purely come down to the chemical difference in the models. So you can see right away that the POP3 star has high luminosity and higher surface temperature for its entire lifetime. Another interesting characteristic is that the RGB tip is much fainter in the POP3 star as compared to the normal star. But it does still go through the core healing flash at the end of the RGB. That terminates the RGB. And that's what we'll be focusing on the next few slides. So here we have luminosity versus time, and here's the helium burning luminosity. So there's this runaway flash of helium burning and in all low mass stars and in the core when they reach the tip, RGB tip. And you can see the luminosity goes really high, 10 to the 10, 10 to the 11 L suns, single solar luminosities, about the luminosity of the galaxy, but for a very brief time. And then they fade away. A normal star, that would just fade away and that will be it for the flash. However, in a POP3 or an ultra metal star, there's a second hydrogen flash. And this occurs because you mix down protons, so hydrogen, into this helium burning region. And this creates very strong burning because hydrogen usually burns at around 20 million Kelvin, but the helium burning zone is hundreds of millions of Kelvin. So you get this massive flash. But importantly, you also get a lot of nucleosynthesis, particularly of light elements. And here I've got surface abundance versus time. This is Z. So here it's Z equals 0. And then later in this evolution, this stuff from this hydrogen flash gets brought up to the surface. And you end up with huge amounts of light elements, in particular carbon, as at the solar level. So you have this 0 Fe star with solar carbon. It's quite a strange situation. And it's unique to these low metallicity stars. So what happens during this hydrogen or proton ingestion? So here's a sort of schematic showing what happens. This is actually a 3D model that I've done 2D slicing. So here we have the stable hydrogen zone, and then here's the helium burning zone, and the green is the protons being mixed down and burned. So what happens when you mix protons into this very hot region? They immediately get captured by carbon-12 to make N13. That decays to carbon-13. Now, when you have carbon-13 at around 200 million Kelvin, you get C13 alpha N, which releases neutrons. And depending how much C13 and how hot it is, you can get more or less neutron capture reactions and therefore produce more or less heavy elements. So we did a sort of rough model of this, and to see how much sort of neutrons we get, what sort of neutron densities. And we get very high neutron densities in these events, so 10 to the 14, 10 to the 15. Comparing this to the AGB gas process nucleosynthesis, which reaches about 10 to the 9, it's much higher than that. But it's less than the R process, the rapid neutron capture process that happens in supernovae of 10 to 24 neutrons per cubic centimeter. So it's sort of in between the S and the R. And this is actually known as the intermediate neutron capture process, or the I process, which was coined back in '77 by Cohen and Rose, but didn't garner much attention back then, and only recently has.
Simon, that's 2 minutes left.
Thank you. So back to this diagram with the SEMP-S and the SEMP-SR. So where does that model fit into this diagram? It sort of lands bang up in this quadrant, which we weren't able to reach before with the S plus R. So the I process seems to do well in explaining these SR stars. So our model only had 320 nuclides, a small network. You really need something like 1,000 nuclides, which is about a third of the entire nuclide chart, to do these calculations. You can do this in one zone, so just a pure network calculation, and this is what Melanie Hampel did at Monash, and you can quite well match the detailed composition of some of these SR stars. So much so that we're starting to call them SEMP-I stars. So the next step in this work is to do fully consistent models. So actually putting in a massive network with something like 1,000 nuclei into stellar structure codes. And so we're doing this with a variety of codes. And I'll just show you a little preliminary result from the Kepler code. So here I've got initial abundance down here. So you can see it's a flat line because it's plotted as a scaled solar. And this is minus 5.5 down here. And this star has a mass of 1 solar mass. I'll just be showing the proton ingestion phase. This is at the metallicity of the Freebel star, actually. So this might be the Freebel star's future once it reaches the RGB tip. You can see I've also got alpha enhancement here because that's what we see at low metallicities. Okay, so now we'll let the pi run. And so initially we have this neutron neutrons being produced, and then you have this neutron capture nucleosynthesis producing things like copper, strontium, but still not much barium and europium then. But then by the end of the pie, proton ingestion, we have this lots of barium, europium, and also lead and strontium. And you can see the classic eye process in which here barium is greater than strontium. So the takeaway message is that these low mass stars at low metallicity can actually produce all these heavy elements from basically nothing, which is interesting for low mass stars. Okay, I'll leave my summary there.
Thank you, Simon. So we have, well, more of a comment as described by Katie on the Slack, which is the location of the boundaries of convection are super hard to define in stellar models, and your work looks quite complex in dealing with numerical artifacts that aren't physical in nature.
Yes, that's definitely a very big problem in these models, and we're very careful about that. And we're using 3D models as well to try and improve the convective boundary treatments. But I'll just make a comment that every stellar code gets these events.
I was wondering, when you increase the number of nuclides or whatever in your code, is it basically like an order n squared kind of problem, or how much more CPU time do you need?
It depends on the code. Depends how the nucleosynthetic part of the code's been done. So, for example, MESA, you can only, I've tried this, you can only put in about 400 nuclei before it will not run. It doesn't go anywhere. For the Monash code, it scales better, so I think we can actually do this.
Gary
depends on the numerics.
Just a quick one, Simon. The proton ingestion episodes, at what metal abundance do they stop happening?
Very good question. I've got a slide here somewhere. To cut down this. Here we go. So this is sort of a summary in the mass metallicity plane. And it's something like -2. So this core flash one that I've been talking about happens much lower, like at -5. And the reason I have those dotted lines is because the convective boundaries, as someone Katie, I think it was, just mentioned, make the boundaries a bit uncertain. But they're you cannot avoid them, but the exact boundary can vary depending on how you treat those convective boundaries.
Okay, but they're not just restricted to extremely, the -6 stars.
No, only certain events. So this is the core flash one, which I just talked about, is more hypermetal core. These AGB ones happen at much higher metallicities.
Thanks.
Okay, so thank you, Simon, again.